Okay, it's 9 o'clock here in California. Good morning and welcome to the first webinar in a series of webinars presented by Molsoft over the summer. We're going to start with looking at ICM Chemist and the desktop cheminformatics tools inside ICM Chemist. The following webinars in the next few weeks will cover the whole range of structure-based and ligand-based drug design, from structure visualization to looking at pockets, binding pockets, to designing drugs or ligand design in a protein structure, through to docking and virtual screening. My name is Andrew Ori, and I'm a senior scientist here at Molsoft. If you have any questions after the webinar, please feel free to email me or call me. During the webinar, if you have any questions, please use there should be a text messaging service on your GoToMeeting panel. You can just type in a question, and I'll try and address it during the webinar, or more likely at the end when we have a bit more time. And if I don't get to your question, I will get back to you by email. Okay, so if you want to follow Molsoft, we're on Facebook, LinkedIn, and Twitter, and YouTube. And on YouTube, there are a lot of tutorial videos. So what we're going to cover today is we're going to build a small database of drugs from a variety of different sources, and we're going to be looking at cyclooxygenase 2 inhibitors. So we're going to build our own database. We're going to build in, read in activity data from the Chembl website database. Then we're going to add property data to our database of drugs. For example, log-P, solubility, polar surface area properties. And we're going to add them to a chemical spreadsheet, analyze the data, and build plots. And then we're going to search our database by chemical fingerprint and substructure, cluster the spreadsheet, and build a focused library. So if you're not familiar with cheminformatics, you may wonder where you can get some of the molecules from. And so this is sort of split up into different sections. So probably the largest database out there is the zinc database. It has more than 35 million compounds from a variety of different vendors. And you can read those in SGF and MOL format, which I will show later on. Another useful website is eMolecules. They have approximately 6 million, maybe more, compounds in there. And it's convenient because you can screen them, and then you can purchase the actual compound directly from them to test. And here at Molsoft, we also we have a good relationship with more than 35 different vendors, and they regularly send us their updates of their SGF files, and we compile them into a database of 9 million compounds, and that's available if you want to use that. And also, you obviously can go directly to a chemical vendor, for example, ChemDiv or ChemBridge, and they can send you the SDF file to look at. And then on the other side of things, we have the PubChem, where you've got chemical activity and the structure, and also the Chembl database. And then there's DrugBank. Both of these are fully accessible from ICM Chemist. You can search them and get a chemical spreadsheet from both of these sites. And there's DrugBank, which contains approximately nearly 7,000 drugs, experimental, and about 1,800 approved. And then there are other databases for biometabolites such as KEGG, HMD, B, and Metlin. Okay, so as I mentioned, we were going to focus on cyclooxygenase 2 inhibitors. And the cyclooxygenase 2 inhibitors are responsible for formation of prostanoids, including prostaglandins, such as prostacyclin and thromboxane. And inhibiting cyclooxygenase 2 can provide relief from inflammation and pain. COX-2 inhibitors are generally members of the non-steroidal anti-inflammatory drug class, and targeting selectivity for COX-2 against other cyclooxygenases reduces the risk of ulcers and is the main feature of two very well-known drugs called Celebrex and Vioxx. They're interesting drugs because there was a little bit of controversy about them. As you probably know, they were approved for marketing, and data from clinical trials revealed that some COX-2 inhibitors caused a significant increase in heart attacks and strokes, with some drugs in the class having worse risk than others. This resulted in Vioxx being taken off the market in 2004, and a black box warning for the other drug, for another one called Celebrex, and some other drugs in this class. So, how can we add information to ICM chemists? So we have we call 0D sort of structures. So these are SMILE strings, and here's a SMILE string for a COX-2 inhibitor called Bextra. And SMILE stands for Simplified Molecular Input Line Entry System. And it's a notation for describing the structure of chemicals using short ASCII strings. So common atoms are represented by elements, which is quite straightforward. Other element charges and isotopes are shown in square brackets like this. Single bonds aren't shown, but double bonds are represented by equals, and a triple is a hash. And ring closure is shown by matching digits here. And you can read the full documentation from the Daylight website. So we're just going to add this SMILE string to ICM Chemist. So we open ICM Chemist and we get a blank panel. At the top here we have a molecular editor button. It's a ring with a pencil. You can click on it, and we can add the SMILE string. So go to Edit, Add SMILES, and we just paste that string and paste the molecule here. This one's called Bextra. Just give it a name. And then we've got options here to convert to 3D, or we can add it to a chemical table. So we click on the chemical table button here, and we're going to give the name, the name of the table is going to be COX-2 inhibitors, and the chemical name is Bextra. So okay, so now we've got the start of our database of COX-2 drugs. Another way of inputting chemical data is from INCHI notation. So INCHI stands for IUPAC International Chemical Identifier. It's a textual identifier for chemical substances. It provides a standard for human readable way to encode molecular information. It's ideal for chemical searching. It's initially developed by UPAC and NIST, and it's non-proprietary. So we have another COX-2 inhibitor here. So if we go back to ICM Chemist, we click here, we just delete the old one, you can select them, go Edit, Add SMILES, INCHI, paste the INCHI key, and now we have the new structure. Give it another name, and then we'll append. We click here to append to the chemical spreadsheet, and so now we have two drugs. Okay. Probably one of the more common ways of reading information is from a mol file. So this is an example of a mol file. They're useful because you can add additional fields for properties. So you can have things like molecular weight or some other property. So if you concatenate a mol file, it makes an SDF file. So SDF file is just a collection of mol files. And when you read an SDF file into ICM, it automatically becomes a chemical spreadsheet. So I have a ready-made, to read in a mol file, you just go File. I have a prepared one for Vioxx. We go File, Open, Vioxx, okay, Open. There was no option to append it, so we now have two spreadsheets. But it's just like an Excel chart. We can just copy the row by selecting it and pasting the row here. And so now we have three drugs. Let's go back. The other way is obviously to sketch it yourself. So this is the Celebrex molecule, and we will go to the chemical editor and sketch this molecule. So we'll go here. So if you just click and drag over your sketch, you can delete it using delete key, and we'll start drawing Celebrex. So Celebrex has a sulfonamide group here, and you notice here we have a selection of bonds and atoms. Atoms can be added using the keyboard if you hover over a particular point and just press the letter for that. And you'll notice on the right-hand side, as I sketch, the chemical properties for this molecule are being calculated on the fly. So we have the formula, we have the chemical smiles for this structure, the Inchi key as you're drawing it, and just and then we have more properties such as molecular weight and high number of hydrogen bond donors, number of hydrogen bond acceptors, and useful things such as the log P, prediction of log P, and solubility, and also some useful prediction or calculation of whether this structure is likely to be what's known as a PAIN structure, which a PAIN stands for pan-assay interference compound, and it's the terminology was developed by Jonathan Bale at Monash University in Australia, and so it will give you an idea of whether this structure is going to be a promiscuous binder or a frequent hitter. So you want to be careful not to include, you don't want to be testing compounds that are going to be reactive or are going to be just going to ruin your screening results. So I'll give you false positives basically. And then there's mole polar surface area. If we drew something with a PAIN, it would alert us with that chemical alert. It's also letting us know about the groups that we've drawn, the chemical groups. So red is bad, generally bad, and green is good. So we also have a prediction of what we define as drug lightness. It's a model based on known drugs compared to unknown drugs, and so this flags up Celebrex as being potentially not drug-like, but it's just a guide. So Celebrex. So we're going to add this to our. So I need the oxygens here. So we're going to add this to our chemical spreadsheet in the same way as before. Click here and add Celebrex. Okay. Another way of bringing in data is to just go to our chemical dictionary here, and you can type in the drug. I'm going to type in a bumetone, which is an old COX-2 inhibitor from 1980s, I think. And then we can add this to our database in the same way. Okay, so now we have five molecules. Okay, so and the final way to show you is that you can also export or take out the chemical information from a 3D structure from the protein data bank. So there is a cyclooxygenase 2 has the PDB code 4COX. So we can search PDB, do a PDB search, type 4COX, and that will read in the structure of cyclooxygenase 2. Okay, and the COX-2 inhibitor is called indomethacin, and it's shown here in 3D. And we can just extract that. There's actually 4 of them in each of the different subunits. So we can extract indomethacin, right-click on it, and say extract ligand as 2D drawing to an existing chemical spreadsheet or table. And go OK. Okay, so that's the final way. Just for demonstration purposes, you can also search the PDB by chemical substructure. So we search by a string with the PDB code, or you can search like kinase. But you can also search by chemical structure. So if you wanted to see, for example, all the structures in the PDB that contain aspirin, type aspirin, close here, and then we run a search at the PDB website, and it returns all the PDB structures with the ID and the structure here. So if we double click, it takes us directly to where that aspirin molecule is in each of these structures. Okay, so that's a sort of side thing. Okay, just going to delete this table because we don't need it. Okay. So this is our first database. Okay. So as I mentioned, we have a direct link to the Chembl database. So it might be nice to see some other inhibitors that bind to COX-2. So we can use the drop-down button, click on Chembl, and we can use we just type COX-2, protein name. You can search by other things such as UniProt, accession number, and other search strings. So if you're unaware of Chembl, Chembl is a database developed by John Overington at the EBI in Cambridge in England. It's a publicly available database of drugs and drug-like small molecules and the database of their targets. It's quite unique because it's focused on all aspects of drug discovery, and it contains more than 1.4 million compounds, and there are over 12 million records of the effects of those compounds on biological systems. So these are all the known COX-2 inhibitors from Chembl. We report 3 different tables to make the data a bit clearer. So Chembl all represents the original activity data without merging and aggregation. Chemical best represents the best activity for each chemical and protein pair. So sometimes there are duplicates, so this is the best. And chemical summary basically puts all of this all this information into one table. So we're going to use the chemical summary. I'm just going to delete the other spreadsheets. So we have the two tables with our drugs and with known inhibitors from Chembl. So it's a chemical spreadsheet, so you can do things like, so this P activation is the minus log of the IC50 value. So we can color, this gives us the indication of nanomolar inhibitor. We can, for example, color by rainbow and apply here. And we can see that the stronger inhibitors are in darker red. The weaker ones are in blue. So it's a chemical spreadsheet, so we can change the views. We can select the mole column, select the activity column, and for example, we can show in grid like this, or you can show in table view like that, as I've shown before. And you can also show in form view. That's the one I meant to hit. So you can browse through your structures like this. Go back to this. So we have the table, chemical table. We can add. It has useful information such as activity. We might want to add some other properties such as molecular weight, polar surface area, and things like that. So we can go to the chemistry menu, go to calculate properties, and we just select molecular weight, log P, solubility, log S, polar surface area, mole area, and mole volume. You could also choose the panes prediction if you wanted to, but I'm just going to go OK. And you see it's calculating for each row. It's relatively quick. So now we have additional rows for molecular weight, log P, solubility, polar surface area, molecular area, and mole volume. So we can use that data to maybe build a smaller database. So for example, we could plot molecular weight versus log P. We click here, there's a plot histogram button. It's asking us for the x-axis is molecular weight, y-axis log P. So plot that, and we can easily select all the compounds that have log P below -6, for example, -5, 5, for example. We can maybe remove some of these. You see it's fully interactive, so if I click here, or select here, the interaction goes over to the table here. We can add other dimensions to this plot, so we may want to add coloring, for example, based on the solubility. So we go apply, and so solubility is colored from red to purple. You can zoom in to the plots and move them around. We could also change the size of the points by, for example, molecular volume, and the larger ones are going to have a larger volume. You can also add another dimension. For example, you can have a shape, and you can choose the species. You can maybe have. You can choose a different option here. Type, which I type, see what happens. Yeah, it doesn't work. So basically, yeah, you can add different dimensions to your plot. So it's going to do that again. like this. And as I mentioned, it's fully interactive, so you can select here. Okay, so if we wanted to select all the ones that had log P below 5, between 0 and 5, for example, you can drag here, and then the selections are made here, and we can right-click and make a new table. So copy selection as new, and make a new database. So we have a new table. I'm just going to delete that. We don't need that. Okay, so that's the plotting. Other things you can do, you can export to HTML. And so if you had 3D representations of this, so you just export HTML and give it a name. And this puts it into HTML format. And you can view it on your web browser. You can also, if it was 3D, you'd have a checkbox here, and you can view the structure in 3D. Just going to delete these plots. You can also mark, if you're sort of eyeballing the table and you find some compounds that are interesting to you, you can select the row and right-click on the row and say mark row. This gives it a red colouring. This one looks like a drug. And then you can always go back to them by right-clicking and choosing select marked row red, and that will select them. Then you can export them to a new table. Like that. Okay, so these are the two tables. I'm just going to move on to chemical searching. So you can use, we have two ways of searching. You can use fingerprints and substructure. So you can search by exact match. So you bring in your compound, you want to find it exactly. Matched by substructure, and we do similarity. You can do similarity searching, and we use the Tanimoto fingerprints. So basically, each structure A and B are divided into small fragments, and then we merge the fragment lists and form 2-bit strings, and then you compare these using a Tanimoto distance, and then you get a Tanimoto distance between 0 and 1, where 1 would be an exact match. So we'll do some chemical searching. So it might be interesting to see if there are how many structures in Chembl have chemical similarity to these known COX-2 drugs. So we can do that by going to chemistry and choose compare two sets. And so we're going to compare the Chembl summary table with our COX-2 inhibitors. And you can do exact match, or we can do similarity. So we'll choose a distance of 0.5. And we just go OK. So it's doing it's comparing this table with this table. And we'll see that so obviously all 6 of these structures have been found. Blue means it's a hit, and we have 2,000 from our table. This table from Chembl has nearly 5,000 structures in it, and from that 2,000 of them, or 2,133 of them, are similar, within 0.5 similarity to these drugs that we had in this table. So we could make a new table. So we'll just go copy selection to new table. And say something like similar 0.5. Go OK. So now we have a new table. It's going to unmark these just for clarity. Okay, so we have this smaller table now. It's only 2,000 structures. But it might be nice to see if there are any drugs in this table that are similar to the most famous inhibitors, such as Vioxx and Celebrex. So we can use chemical searching to do that. So there's a button next to the button with the editor. We can click on here, and this is the search. So we know that both Celebrex and Vioxx have, or one has a sulfonamide group and the other has a sulfonyl group. So we would be interesting to see which ones match, if we can find some more with similar substructure. So to do that, we can start sketching a chemical search here. So if we draw the part of the sulfonamide, we draw the sulfonamide first. Okay, 0. And we'll say that we want this atom here to be a member of a ring, similar to Celebrex. So right-click on the atom, and we get a number of different filters, such as ring. We could say we want that atom to be part of one ring, or 2 rings, or 3 rings. We want that atom to be part of a 5-membered ring, a 6-membered ring. We want that atom to have a charge of a certain definition. We want it to be connected. We'll look at that later on, or an attachment point. But we're going to just say we're going to say this is an attachment point here. Okay. So this is our query. You can actually read in the SDF file here and search that SDF file against another SDF file, but we're just doing a small query. You can search. We're searching against a table. We're going to search against a similar 051. Or you could search against an SDF file saved on your computer. There's another product we have called Molcart, which is a chemical cartridge, which is useful if you've got millions of compounds and you want to build target-specific libraries. So you can choose to search by fingerprint similarity or substructure, and just go. And then there's some options such as just count how many hits you get, or save them to a file, whatever. So we'll just go search. Okay. I'm getting lots of questions. I think I'm going to try and address them at the end. Let me just double check. Yeah, so we did that search. And we've got some hits. Let's have a look at the hits. Let's get a table called result. And you see that we have a hit with a sulfonamide. But unfortunately, we're getting some of these the sulfonamides like in a linker between 2 different chemical groups. It would be nice to remove those and just find the ones with terminal sulfonamides. So let's change our search criteria a little bit. So we can say let me just double check. So if we change the connectivity of this nitrogen, that would reduce the chances of finding of this being in the middle of a linker region. So this would be a terminal. So we can make this a terminal nitrogen, and we can say this nitrogen needs to be as drawn. So we can say we right-click on the nitrogen and choose connectivity. We don't want it to connect it to anything else. We can just say as drawn. So just be a terminal nitrogen. So if we run this search again, we should now just find the terminal sulfonamide groups. You can see they're highlighted in green. And our table now is only 215 rows in length. And the original one was 5,000. Then we brought it down to 2,000, and now you can see at the bottom, it's shown at the bottom here. So now it's 215. But it'd be nice to just increase this a bit and bring in the Celebrex ones, which have rather than a sulfonamide, they have a sulfonyl group. So we can do that by changing the search criteria again. So we go back to the chemical search panel, and we just edit this. So we'll change it to right-click, and you can go to custom, and you can say I want a nitrogen there, N, and or a carbon for sulfonyl, and this is the this as drawn D1. So go OK. Now we should find, if we run the search, we got a few more hits. It's actually increased to 1,300. And we should now have sulfonamides and sulfonyls here as well. Okay. So we can also say add additional search criteria here. So this adds filters based on columns that you have in your table. So we could say we want only structures that have a molecular weight less than or equal to 500, and we can add another condition, log P less than 5. So it's going to search this and add these filters as well. So we go search, and so we have a smaller table of just 1,100. So these are the way we search. Okay. So the next thing we want to just look at is chemical clustering. So you have a table, and you can cluster the table simply by clicking on this clustering button. Let's do it in the larger table, the 5,000. We can cluster. Go OK. So this can cluster by substructure. So now we have this fully interactive tree on the right hand side. We can change the distance of this tree by dragging on this bar. You can see we have different branches. And say, for example, this is the results of a virtual screening, and you've got a large number of hits, and you want to select a diverse set of compounds to send to your collaborator to test. You can take, for example, a center representation of each of the branches, and then you get a nice, diverse but smaller database. So to do that, you right-click on the tree and choose Select Centers like this, and then you see that they're selected here in blue, and they're also in blue here, and we can right-click and choose that option again to say New, and you can just say Centers. This is centers at 0.3, distance of 0.3, so for example. So okay. You can also change the right what's on here, so you can. It's at the moment it's got the Chemical ID, but you can change the record labels. Choose column. So we could add the name. We got the name already. Synonym. Go OK. So it adds the. So we got a few with the drug names here. Okay, so that's the chemical clustering. You can also select centers by a particular value. So you could, if you had, for example, a virtual screening score, and generally the lower the score, the better. So you could say by minimum score or by minimum log p, and that will select based on that. Okay. So the final thing I'd like to show is how to build a combinatorial library. So here we built our own library with a variety of sources, from drawing our own structures and reading in from other databases. But you can also use a combinatorial library design. There's different ways of doing it. You can read in a Marcouche structure, sketch a Marcouche, and where you have another table with R1s, R2s, and R3s for each position. I can show that. And there is also a reaction base, so you can draw your reaction and your product with your R1s and R2s and R3s. We'll show both of these. So I'm just going to get a new chemist session. Okay, so here I have another chemist session. In the distribution, we have an example called example_enum for enumerate. So here we have the scaffold of our drug series. We know this scaffold is a decent scaffold, and we've also got a variety of groups for each position of the scaffold: R1, R2, and R3. The scaffold you can sketch here. As before, you just right-click on an element and then add R1, and that will load it. So to generate this library based on these substituents at each point, we go to chemistry and combinatorial chemistry, enumerate by scaffold. So, and it asks which of the tables contains the scaffold, and it's actually called scaffold, which is, and you could have multiple scaffolds, and we're just using the one in row 1. And then for each R1, for each of your positions on your Marcouche structure, you can choose a table. So we have R1, mol, R2, and R3. And you can add certain filters if you wanted to, and then you can enumerate. And this builds the library, the new library. Okay, so this is the result. We have the core substructure with these substituents on each point. And the new library contains 1,320 elements in it. Okay. So it might be a real-life example may be that you have some results with, so basically you've made this library and you've tested the library, you got some good hits, and you want to see which substituents are contributing to the activity and which substituents lose the activity. So we can build a structure-activity relationship table. So, just a second. So here I have a set of results. I just read in a table. I went to File, Open, and I read in a table with the data. So I have an extra column with the KI values on here. So basically, we can split, and we know that each of these structures have this. Sorry, just 1 second. Open the wrong one. Has a common substructure from our original from the original table, from the original scaffold. Just gonna find. And so we can decompose this table based on that Marcuse structure. Okay, right. So yeah, so this is the table. It's just got IC50 values in it. I'm just going to delete these. Oh, it's a different thing. Okay, so it has a common structure. So we go to chemistry, and we choose combinatorial chemistry, and we can choose R group decomposition. Okay. So the scaffold that we're going to decompose this database by is called scaffold. So we use the drop down, choose scaffold. The index is 1, it's the first row. And the table for decomposition is the screening data. And the column we're going to decompose is obviously the mole column. We're going to generate a single SAR, structure activity relationship table. We go OK. And now we have this useful table. So we can sort a column by IC50. And we can see that many of the lower ones, they just have a carbon at this position in R1 with a good score. And so you can use this table to try and see trends in which substituents are useful at each position and based on activity. All right, and finally, you can generate a combinatorial library based on a chemical equation. So we go to in a reaction. So we have the reaction here. So we have a pyridine synthesis reaction. You can draw the reactions in the same way as before. We have for this arrow, there's a button here for the arrow. So you draw the reactants and the products. And so in the same way as before, we have the reactants for the reactant 1, and we have reactant 2 here, and that will generate the. Okay, so we go to chemistry, combinatorial chemistry, and enumerate by reaction. The reaction is called this one. There we go, OK. In the same way before, the reactants 1 and 2, and then you can mark unused reactants and other things. So you go enumerate. And there we have a new database based on that reaction. So this time it has 360 structures in it. Okay, so that covers basically most of the things. In ICM Chemist, there are other what you can generate conformers, stereoisomers. You can look at the ligand energetics. For example, you can merge 2 tables, select duplicates. Clustering we looked at. You can standardize a table so you can remove salts and explicit hydrogens and other things that you don't like. You can also build prediction models, and that will probably be a webinar in the fall. So we have a big new product called Molscreen, which is a product containing 900 models based on data from Chembl. And these are ligand-based models that you can screen against. And you can actually build your own models in ICM Chemist, and that will be another whole webinar in itself. So I'd like to leave it there. The next webinar will be in a couple of weeks' time, I think, and it's called Interactive Drug Design using the ICM 3D Ligand Editor. So we're going to show how to you bring in a structure, you can display the binding pocket, and then you can start using the binding pocket to design new molecules. Or you can use your chemical intuition to try and design new structures. You can redock them, and it's developed between. So, for example, here it's showing that there's some unsatisfied hydrogen bonds, so you might want to build towards, or maybe to one of these side chains. And here it's showing that so then you can edit the ligand in 3D. So that's the whole. That's in a couple of weeks' time. So if you go to our website and go to the same place where you signed up for this webinar, you can find the link for that. Okay, so thank you very much. I've got some questions that I can try and answer. Some of them I will answer via email. I think I've got your name, so should be able to do that. Had a question. So yeah, there was a question regarding the Kemble. Some people are using an older version of Chemist. This Kemble search is available in version 3.84, which we're officially going to release in the next couple of weeks. But if you want to try it, I can send you that version. We had a question, how does ICM handle null data in certain rows? Especially well calculated. Yeah, it will give you a it will say ND in each of these. If there's no data, it would provide it will say ND, and so it will be a sort of a null value. We had a question. What is the source of the compounds to build the combinatorial library? So I guess for you talk about the substituents for that. So we have, and while people are still here, if you want to ask a question, if you put your hand up, I can probably open your mic and you can ask the question over the internet. Just realize this. I think there's a way to raise your hand if you have a question. So there was a question I was answering about the R1. So we were looking at the example enumeration, and we have the R1s here. So we have, inbuilt in ICM, there are some default substituents that you could use. You could read these from a. There are also in Molcart there are building blocks that you could read in and use. We have our own, as I mentioned, our own substituents as well, or you could sketch them. So there's like 3 different ways. We had, sorry, I'm going from the earlier. It's a bit annoying, this setup, the GoToMeeting. It's okay. Yeah, sorry. So, do you have a large chemical of reactions? We do. Not by default. We do have we have a variety of reactions for covalent docking. We don't have that many pre-made, but you can sketch them yourself here in the editor. Is it possible to do R group decomposition with a set containing different cores? The only way to do that would be to have different, in this scaffold table, would be to have different scaffolds for each of your different cores, and then rerun it each time. Can I export the database to SQL? It can be saved as, well, you can export to HTML, you can export to Excel, you can save as SGF and Mol, but it can be imported into our Molcart database, which is a SQL. It's based on SQL, basically. So I had a question regarding products. So is this available in ICM Pro? Many of the chemical sketching things are in ICM Pro, but if you have the VLS, ICM Pro plus VLS component, then you have all of these tools because they're automatically included in that. So if you have ICM Pro plus VLS, you'll have that. How to generate attachment points for the Marcouche. You draw your molecule, or you have a set of molecules, and you can automatically assign them, or you can do it yourself by right-clicking, say attachment point, and then append it to a new table. Okay. Can our internal database be integrated with ICM? Yeah, there's no reason why not. It's just it depends what format, but most likely it's in SDF format. We have Molcart, which is a separate product, but if you just want ICM Chemist, we have a way of building databases directly inside ICM Chemist, and you can do chemical searching of large databases using it's called multi format, and you can do that. Okay, yeah, there's some other questions I'll try to reply by email. Let me just see if there are anything else. Okay, so I'd like to thank you very much for your time, and if you have any questions afterwards, please feel free to email me or call. Okay, so I'll leave the session open for a few more minutes, and if anybody else has any questions. And thank you for your time. Please join us at the next one. Let me just find the date. There was a question about training materials in the GUI. If you go to molsoft.com/GUI or go to Molsoft and go to support and manuals, for ICM Chemist, you'll find the tutorial. So a lot of what we just did is in there. So the next workshop, next webinar is going to be on 23rd of July, and that's the 3D ligand editor. So just go to Molsoft's event.